So as I was mentioning just a few minutes ago, I uploaded this new set of notes onto B courses. Sorry to be late with that. I've been having trouble with B courses this morning. But you'll have these notes as of today. So let's hide the images and then we can begin. Okay, so finally we're ready to put everything we've learned so far into service in the formulation of plasticity theory. So let's go back to our first lecture and recall the lessons learned from a uniaxial test where we plot uniaxial stress, say T, against the so-called logarithmic strain, which is the preferred measure used by metallurgists for representing data. We had that discussion at the first lecture. Remember that we had the logarithmic strain, natural log lambda, is the sum of an elastic logarithmic strain, natural log lambda sub E, plus natural log lambda sub P, where lambda and E or lambda P were the stretches. So the stretches combine in this manner to produce the overall stretch of the uniaxial bar. And we interpret lambda P as the actual stretch that exists in the absence of stress or load, right? So that lambda sub E, the elastic deformation, is equal to 1 when there's no stress. That means essentially the elastic strain corresponding to 0 stress is 0. There's a natural log. So this is we'll extrapolate these ideas from 1D to 3D. Another lesson from that 1D test is that the elastic property of the material, in this case it's only the Young's modulus that enters in the uniaxial test, is very nearly insensitive to plastic deformation. So if we unload after yielding, then the elastic modulus remains fixed no matter what the plastic strain is. And that's a manifestation of this microstructural observation that you can find in the work of G.I. Taylor going back many decades now, is that the so-called plastic slip. So here's a cubic lattice, let's say. Plastic slip is facilitated by the movement of dislocations, as we mentioned previously some time ago. In the course of that slip, the basic lattice structure is unaffected by this plastic slip. So a cube remains a cube and so on. And for that reason, the elastic properties, which are encoded in the lattice structure, are also very nearly insensitive to plastic deformation. So we will embed these observations into the formulation of the theory. So the first thing we need to do immediately is generalize to 3 dimensions. We had at the top here this notion that lambda is lambda E lambda P. In other words, the overall deformation of the material involves the product of the elastic and plastic stretches. Let's see if we can generalize that notion. Well, I'm sure you've all heard of this decomposition. Deformation gradient can be decomposed into an elastic part and a plastic part. That's the 3-dimensional generalization of what we've just said. Maybe an easier way to think of it is this. We have the actual state of the body at time t, configuration kappa t as usual, the material point in that state. And we imagine unloading to an unloaded state. We'll call that an intermediate configuration, kappa sub I for intermediate. And the deformation required to put this intermediate configuration back into the current configuration, we'll call that deformation H. We interpret that as the elastic deformation. In other words, just as in the uniaxial test, the elastic deformation, elastic strain, is that which is required to go from this unloaded state back to the current state. Okay? So this would be the overall natural log lambda right here, this value, if you see my cursor. So the difference between that and this plastic strain is natural log lambda E, that's the elastic strain. So lambda E would be the elastic deformation. This is the same idea here. This H, which we can call also F subelastic as a more conventional notation, is the deformation gradient required to restore kappa I to the current configuration. This state is not related to the reference configuration that we choose for the purpose of analysis, right? For that, we need the deformation gradient to take us to the current configuration at a material point. To go from this intermediate state to the reference configuration, we need another map, call it K, which would be the inverse of FP. In other words, the plastic deformation would take us from the reference configuration to this so-called intermediate unloaded configuration. This would be FP. Going in the reverse direction means FP inverse. So we can write that this way. So H then would be F preceded by K. We first map the point by K, then map the point by F, and we arrive at H, okay? That's just another way of writing F as FE, FP, where FE is H and FP is the inverse of K. So to avoid all this subscript notation, FE and FP, I'll write that G, right? So F plastic is G, which is K inverse. F elastic is H. Okay, so earlier on we introduced the idea that we can always choose an occupiable reference configuration, one that could in principle be occupied by the body. That's for example, the body could not occupy its mirror image, right? We could use the mirror image of the body as a reference configuration, but then it's not a configuration that could actually be occupied by the body. So here we have in mind that the reference configuration, for example, could be some initial configuration of the body at some time t0. We know then that the determinant F is positive. We'll assume the same, that when we unload the body, we're achieving to zero load. We're achieving a configuration that not only could be, but actually is occupied by the body. So det H is then positive. So from this formula then, the det of this is the product of the determinants det F and det K. So det K must also be positive then with these assumptions. So we'll simply impose these requirements at the beginning. Now, if we look back at the uniaxial test, the presumption is when we unload here, lambda E corresponds to a state of zero load in a bar with a uniform state of stress in it. Zero load means zero stress also, right? The difficulty is that we can't really do that for the following reason. So the presumption here in this argument is that kappa I is achieved by unloading and is supposed to be stress-free to preserve the analogy with the uniaxial case. The problem is that we generally cannot unload a body to zero stress everywhere. And the reason is precisely because due to plasticity, we can have dislocation in the material. So in reality, these dislocations generate residual stresses that remain even after we remove all the loads from the body, the traction and the body force. So because of the passage of dislocations, for example, we have a dislocation, for example, an edge dislocation will induce a lattice distortion in the neighborhood of that point there, which we call the core of the dislocation. This would be the so-called core where the dislocation line ends in the crystal. The presence of the dislocation induces a distortion of the adjacent of the lattice in the nearby neighborhood of that core. And the distortion of the lattice is what produces stress. In order to distort a lattice, you're straining the lattice and you're causing stress. So it's inevitable that when you plastically deform a body, except under extremely special conditions, you will produce dislocations in the body. These will cause the material to be stressed, even though there's no traction or applied to the boundary of the body or no body force. So we have to take this into account somehow. So in reality, the residual stress is due to the lattice distortion caused by dislocations, and also possibly other defects like interstitial atoms from a foreign substance lodged in the lattice will cause a distortion of the host lattice in the neighborhood of that interstitial atom, where you might have a vacancy, a void, caused by diffusion of interstitial atoms outside, diffusion away from the material. That would create a hole in the lattice, and the lattice would distort in the neighborhood of that hole in order to, in response to that vacancy. So dislocations are not the only kinds of lattice, so-called defects, we could call them defects, but there are other kinds as well, interstitial atoms and vacancies being the primary important defects in crystalline materials. You could even have so-called rotational defects. Those are called disclinations, and we can hopefully have an opportunity to talk about those later on in the course. So as I say, these defects and therefore associated lattice distortions persist even in the absence of load. So we cannot, in principle, we cannot actually unload the entire body to a state where the stress is zero everywhere in the body. But we can do the following. Let's look at a process, a hypothetical equilibrium unloading process, where we unload the body while maintaining equilibrium. Well, we can then assert that the mean stress over the body is actually zero. So in continuum mechanics, we always teach the mean stress theorem, right? So I'm assuming in 185 or 287 or the equivalent, you've seen the mean stress theorem. So the mean stress times the volume of the body, say in current configuration, the mean Cauchy stress would simply be the volume average of the Cauchy stress distributed over the body. The mean stress theorem for equilibrium tells us that that's just the symmetric part of this right-hand side, this parenthesis. The traction integrated over the body, tensor product, the position field on the boundary, and the volume integral of the body force, tensor product, the position field times the mass density. Okay, has everyone seen the mean stress theorem? I'm hoping that's a yes. If not, it's easy to prove, and you can find it in any standard continuum mechanics book. Okay, so if we don't apply any traction at all to the entire bounding surface of the body, there are no tractions acting, and we don't apply any body force, then the mean stress is zero, even if the local stress is not zero. Well, what can that do for us? Well, the mean stress theorem presumes that the Cauchy equations of motion are satisfied, or equations of equilibrium, which means the stress is differentiable so that it has a divergence. If it's differentiable, then it's also continuous. The differentiable function is also a continuous function. So it's consistent to assume that the Cauchy stress is continuous as a function of position in the material. There's something then called the mean value theorem, which is another way of saying the localization theorem, or it's the basis of the localization theorem in continuum mechanics. Mean value theorem says for a continuous function, there is some position, some place in the domain, in the configuration kappa t, at which the local stress is equal to its mean value. And you can convince yourself of that by, in the one-dimensional case, draw a function f versus x. Just draw a function which is continuous over in some interval of x values. Pick out the mean value, and you'll see that indeed there is a place in the domain where the actual function is equal to its mean value. And that's called the mean value theorem. That's true for any continuous function. So because in this case where no loads are applied to the body, after all, to achieve this so-called intermediate state, we've agreed to remove all the loads from the body. Therefore, the mean stress is 0 after we've done that. Therefore, there is a place in the body where the actual stress is equal to 0. Some point x bar, maybe more than one. So there exists a point, perhaps more than one, but at least one, where the actual stress is equal to 0. Okay, how can that help us? Well, let's introduce a notion of the size of the body. So form the difference of all position vectors in the body and maximize that over the entire body. We take the supremum, which means essentially it's the least upper bound or the maximum of this over the entire body. Form all the position differences that you can in the body, and then pick out the largest one. We'll call that the diameter of the body. Even if the body, that makes sense, even if the body is not a sphere, it's still, this notion of diameter is still applicable. Okay, if we were able to make our body arbitrarily small, in other words, make its diameter go to 0, then that means every point in the body would get closer and closer to every other point in the body. In particular, every point would get arbitrarily close to the position x bar where the stress is 0. So if we could make the body arbitrarily small, we would then force the local stress to approach 0 everywhere in the body. Okay, so in fact, we can't do this because we're stuck with a body of finite size, but we can do the next best thing. What we can do is we can apply the mean stress theorem to an arbitrary subvolume. Call it P sub t of the current configuration. Now, we can imagine surgically removing this P sub t from the rest of the body and removing all the loads on P sub t. Okay? So we can imagine splitting the configuration kappa t into a number of subbodies and unloading each one of those separately. Okay? If we can make those, if we let the number of subbodies go to infinity, then the size, the diameter of each one of them is tending to 0. So in each subbody then, whose size is arbitrarily small, the local stress tends to 0 for each unloaded subbody. Okay? So we could imagine cutting the body into arbitrarily many, essentially infinitely many subbodies of arbitrarily small size approaching 0. So we surgically remove all of them from the body, unload them individually. The local stress in each subbody then approaches 0 as the size of those subbodies approach 0. Okay? So in fact, this looks like a purely hypothetical exercise, but in fact, this is exactly what people do to measure residual stress in a body experimentally. If you have a part and you want to know the residual stress state in that part, what you do typically is shave off a small piece of that part and allow it to relax to zero stress in accordance with this discussion. Of course, you can't make that part that you shaved off, you cannot make it infinitely small, but you can make it fairly small, very small compared to the overall size of the body. After shaving off that small piece and unloading it, the stress is approximately zero in that piece, close to zero. So then you can look at its shape. You can look at the shape that that sliced off piece has, unloaded piece. And then by mapping, if you have a constitutive equation for the body, mapping that piece back into where it fit before you shaved it off, that would be the deformation. Having the constitutive equation, knowing the deformation, you then know what the stress was before you shaved it off that little piece, and that would be the residual stress in the unloaded overall body. So this is in fact the experimental this furnishes the basis for experiments designed to determine residual stress. They don't give you exact answers because you can't you can't cut the actual body into infinitely many pieces of zero size, but you can approach that asymptotically. Okay, so of course, after you've shaved off each little piece will undergo its own distortion and change in shape. So if you try to fit these pieces back together like a puzzle, they won't fit back together anymore, right? Because they all undergo independent, separate changes of shape. You can only fit them back together by stressing them so that their shapes all conform back to each other in the actual body before these pieces have been separated. Is that more or less clear what I'm saying? Okay. So the individual unloaded pieces will be shaped differently in such a way that they don't fit nicely together again. And so they're disjoint, right? That you can't fit them together. So they don't fit together to form a connected region in three-dimensional space, or three-dimensional Euclidean space, which is where the original body resided. Okay. So we have infinitely many stress-free subregions of essentially infinitesimal size. We can't fit them together to form a connected region in a smooth, continuous body in Euclidean space. So that means there's no global relaxed configuration of the body. There are only these local relaxed configurations. Okay? So this intermediate, each of the intermediate, let's say this intermediate configuration we've been talking about is really the union of all these disjoint little tiny pieces that don't fit together quite. Okay? So we can achieve the zero stress condition associated with kappa I, but we're not then getting a global configuration of the body. We have all these arbitrarily many disjoint stress-free subbodies. So we can't, although we cannot fit these together in our Euclidean space, we can nevertheless fit them together in a non-Euclidean space, a non-Euclidean manifold, which we'll discuss. Okay. Okay, so the situation is analogous to the following. Imagine you have say a plate a circular plate under compression all around, and you cause the plate to buckle, right? For that plate to remain, so the buckling process, say, will alleviate stress in the plate. In order for the plate to stay Euclidean on a flat plane, flat space is Euclidean, two-dimensional space, in order to relieve the stress and stay in a Euclidean space, you have to chop up the plate into little pieces. But if you allow the plate to undergo a curvature, so that intrinsically, as a two-dimensional continuum, it's now residing in a Riemannian space, a non-Euclidean space. The stress is relaxing. The stress is relaxed, but it's relaxed by putting the body into a non-Euclidean space from the intrinsic two-dimensional point of view. Of course, that whole thing resides in a three-dimensional Euclidean space, right? But if we want to look at the mechanics of this two-dimensional object from an intrinsic two-dimensional point of view, this relaxation process has moved us from a Euclidean space, the flat plane, into a non-Euclidean two-dimensional space, which is the curved surface associated with the buckled plate. So that analogy, I hope, helps to understand what we're doing here. And in fact, precisely this analogy was used in the early days of the interpretation of plasticity from the point of view of differential geometry, going back to the 1950s. And the main originator of that idea was a fellow named Kondo, a Japanese mechanical engineer, applied mathematician, back in the 1950s. Okay, and then later people were really attracted to the geometric interpretation, and there was a lot of work done to advance this subject, and we'll try to take advantage of that in this course and make use of it. So, having relaxed, having chopped up the body into a million pieces, let's say, there's no longer a position field in the body, right? So the deformation that takes us from the current configuration to the relaxed state we call H inverse, right? That's the inverse elastic deformation gradient, or it's also the plastic deformation, G, that takes us from the reference configuration to the same state. But there's no position field for the body, because the body, I mean, you only have a collection of points in space, right? There's no field, differentiable position field defined on a body anymore, associated with the intermediate. These disjoint states we call the intermediate configuration. So that means this, although we can do this locally at the scale of the individual points, we cannot integrate this. In other words, this is not an exact differential. There's no neighborhood of a material point in one of these relaxed neighborhoods, or relaxed parts, because they're infinitesimally small. There's no neighborhood in which you can define a gradient, because in order to define a derivative, you need a neighborhood of a point. But everything has been collapsed down to the scale of one point, or infinitely many points. Right? So everything is collapsed down to the scale of a point. So there's no neighborhood in which you can use to define a gradient. Right? So that means this G is not the gradient of anything, and neither is the H inverse the gradient. So the point is, in order to make this process work, we have to allow the idea that the G, or the F subplastic, FP, is not itself a gradient. Of course, F is a gradient. The overall deformation, there is a deformation field on the body. We can take the gradient, and that's the deformation gradient. So F is a gradient, but the individual factors, F plastic, we call FP or G, that is not a gradient. And neither, of course, is its inverse, K. If K is not a gradient and F is a gradient, then H, which is the product, is also not a gradient, and neither is the inverse of H. So in order to push through this concept of a relaxed intermediate configuration, we're forced to accept the notion that this decomposition of the deformation gradient into an elastic part and a plastic part, which is the inverse of K, we're forced to allow H and K to be not gradients. They're just tensors. Okay. In other words, G d capital X is not an exact differential because there's no chi. We can use it to define a d chi, I, but we cannot integrate this to get chi because there's no chi field associated with the intermediate state. So that means if we integrate G d capital X around a closed loop, let's say in the reference configuration, capital gamma, we're not going to get 0 because this is not an exact differential. We'll get something we'll call B associated with that loop. And that's called the Berger's vector induced by plasticity. And we'll relate this shortly to a dislocation density. So this is the Berger's vector associated with a distribution of dislocations contained within, associated with this loop gamma. Now, in this intermediate configuration, it's just a collection of, in principle, infinitely many discrete points, so that we cannot draw a curve in this intermediate configuration, right? Because you have a dust cloud of points, and there's no curve connecting them. In order to connect to make a curve, you have to go into the vacuum in between those points. And that means leaving, that you cannot construct a curve within the actual material in the intermediate configuration. You can do so in the reference configuration. And you can also do so in the current configuration. So in the same way, this H inverse dx is not, if we look back here, H inverse dx is the same thing here. It's also not an exact differential. Even though d small x by itself is an exact differential, H inverse dx is not, because H inverse is not a gradient with respect to, of anything with respect to small x. Okay, so if we draw a loop, a closed curve, say small gamma, in the current configuration, then the closed contour integral of H inverse dx will also not be 0. We'll call this small b. It's another way of defining a Berger's vector, so-called Berger's vector, associated with that loop in the current configuration. Let's stipulate that this loop, gamma, is the deformed image of this gamma here. In other words, little gamma is what you get by mapping this gamma as a material curve by the deformation function, the overall deformation of the body that takes you from the reference to the current configuration. Then, we can change the variable by noting that d small x is f d capital X, and that change of variable means now we're integrating over capital gamma, the closed loop in the reference configuration, and we carry this H inverse f, that this product is nothing but G, the plastic deformation, and this loop integral is just the capital B. So essentially, we define, these are both the same Berger's vector, right? Okay. Well, we can go back to our discussion of differential geometry and give this this idea an interpretation in terms of differential geometry, and see how we can then associate with this so-called intermediate state, which is just a dust cloud in Euclidean space. We can glue it together in a non-Euclidean space into a manifold. But that manifold will be necessarily non-Euclidean. So let's look at a differential geometric interpretation of this story here. So the notation is not ideal. I've used capital G for plastic deformation. That's a tensor, a second order tensor. Before I use capital G sub I as a natural basis vector is associated with the, induced by the convected coordinates in the reference configuration. So bear in mind the capital G sub I are 3 vectors, whereas capital G without any subscript is just a second order tensor of the plastic deformation. So just please be mindful of that notational issue, okay? So here, these are just a usual natural basis in the reference configuration. Again, induced by convected coordinates. So we could imagine painting a grid of coordinates on the reference configuration. We'll call those our kind of curvilinear coordinates. Then that painted grid deforms with the body, then the convected coordinates, okay, as usual. Now, remember before, we used the deformation gradient, that maps capital G sub I into small g sub I, right, from last lecture. We could imagine instead mapping the same capital G sub i's by the plastic part of the deformation gradient. When we do that, we get three vectors. I'll call them, say, small m sub I. Okay, I have to name them something, so I'll call them small m. By the same reasoning that we used to obtain this expression last time from the deformation gradient, we can then construct a representation for tensor G, the plastic part of the deformation, m sub I, tensor product G super I. The same procedure exactly. And that's the inverse of our K. K maps the intermediate to the reference. G maps the reference to the intermediate, okay, locally. Okay, having introduced these vectors now, we can use them, as we did with the small g's, we can use them to define a metric just by taking their dot products. A symmetric metric m sub ij associated with these vectors that we've induced here. And if we do that, we can interpret, so this would be the right Cauchy-Green deformation tensor associated with G instead of F, right? G transpose G. We saw before that the actual right Cauchy-Green deformation, F transpose F, had covariant components G sub ij. In the same way, G transpose G with this representation will give you M sub ij instead of G sub ij. So we can interpret, as we did before, this induced metric associated with this intermediate configuration. So these are vectors now in the intermediate configuration, right? We can associate that metric as the covariant components of G transpose G. Now G has a positive, tensor G has a positive determinant. G transpose G is therefore a positive definite. Therefore the matrix M is a positive definite matrix, and its determinant will be positive, just as usual. We're only repeating our discussion except applying it now to these vectors M. We can then generate a dual metric, the inverse matrix of the original metric, and use it to define the reciprocal or dual basis M super I associated with the natural basis M. Now the M's here are not the G's were the derivatives of these, and the small g's were the derivatives of the small x with respect to the coordinates. There's no position vector associated with the intermediate configuration. Therefore, the m's are not the derivatives of anything. Right? You cannot write mi as something comma I, because there is no something, there's no position field to take the derivative of. Okay? And that's the essential difference between what we had before and what we're doing now. So nevertheless, we can use these small m's vectors to define a connection in the way that we've done before. So we'll call the connection coefficients based on the small m. These are defined in exactly the same way that we did in our conventional Euclidean space. We'll call them gamma hat, because I'm running out of notation. The gamma notation is extremely well entrenched in the differential geometry literature. We always use gamma as a notation for the connection. So we'll keep that and just put a hat on top to remind us that it's different from the connection we've been using before. The one with the current and one with the reference. This is different. So in the usual way, we can use the m's as a basis elements. These are and then expand this by writing this as the projection of the mi comma j into the dual basis multiplied by the natural, by the original basis. I won't call it natural basis anymore because it's not the derivative of any position field. And we get this representation here. Now, if you go back in your notes, I think page 48, I believe, we define the Riemann tensor this way, right? We can introduce a Riemann tensor associated with the gamma bar connection that we've just introduced. Whenever a connection has this form, the associated Riemann tensor is identically 0. We've seen that before. And we've seen that without making any use of the idea that these vectors were the derivatives of a position field. They're just, whenever the connection is of this form, the associated Riemann tensor associated with that connection is 0. So this manifold we're constructing is flat. It has 0 Riemann tensor. However, it has a non-zero torsion because the skew part of the connection in the lower subscripts, see if M were the, if the MIs were the partial derivatives of some position field, this would be the comma ij of that, and then you would have symmetry in the subscripts, but that's not the case here. So in general, we do not have symmetry in the subscripts I and j. So we have, if we skew symmetrize in the subscripts, we will not get 0. We'll get something called the torsion tensor, which you're looking at now in your new homework. And that's just M super K dot M I comma J with the I and J skew symmetrized. Okay, so we can see what those are in terms of the plastic deformation. MI, we had plastic deformation operating on G sub I. Take the comma J of that, you do this. These are just our referential connection coefficients times G sub K. Mapped by G, you get M sub K back. These are nice. These are symmetric in the subscripts because the capital G's were the derivatives of the reference position field, right? That was a Levi-Civita connection, which is symmetric in the subscripts. But here we have tensor G comma J operating on GI, and there's no reason to expect that this would be symmetric in I and J. So in general, this is not 0 for a given plastic deformation as a function of the coordinates. When you take the partial, you do this operation, there's no reason to why you would expect to get 0. So that means this, these vectors induced by mapping the referential vectors into the so-called intermediate state by using the plastic deformation, these can be associated with a non-Euclidean geometry. It's flat, 0 Riemann tensor, but it has torsion. Okay? So therefore, this manifold we've now constructed is not Euclidean. By the way, in the old days, going back almost 100 years, this kind of non-symmetric connection was first discussed by a geometer, a mathematician named Weizenbach. And so it's since come to be known as the Weizenbach connection. This was also plays a prominent role in the study of differential geometry by a very famous French geometer named Cartan, C-A-R-T-A-N, or Cartan if you want to anglicize it. And there's a whole geometry created by Cartan in which this notion of torsion figures very prominently. And in fact, he had an influence on Einstein, who later sought to generalize his relativity to include not only Riemannian curvature, but also Cartan torsion. And there have been a number of attempts to generalize relativity to incorporate the idea of torsion, associating torsion with strange objects like black holes in space and space-time and so on. But whether or not those have been successful is open to question. Notice, let's go back a minute. If G were a gradient, just like a regular deformation gradient, that would mean these vectors, Mi, would be the gradients of something, the partial derivatives of something, right? So U would be like a position field in the intermediate configuration. So that the G would then have this form, U comma I tensor product G super I. In this case, we would have, in this formula here, we need the G comma J. We could work that out. That would be U comma IJ. Let's see, I'm using a K here. I'm changing the this to a K. That'd be U comma KJ tensor product GK minus the comma J of G super K, which would give you this, and then form the product, this combination here, G comma J on GI, would give you U comma IJ and this would be completely symmetric in the subscripts, right? If you have a C2 U field. Then we would have zero torsion. So you see that you only get zero torsion when G is itself a gradient of something. But if it's not, then we can expect to have a non-zero torsion. Okay. Okay, so we've belabored this now repeatedly, that we have a manifold that's, we can relax the body to zero stress in a space globally. We can do it globally. But the price we pay is we have to abandon the Euclidean nature of the space and instead have a space with a torsion, okay, which is a non-Euclidean concept. Okay. So in fact, these MIs we've introduced, they constitute a basis, right? You can think of them at any given material point as a tangent space, the space tangential to this non-Euclidean space. Just like on a surface, you can introduce a tangent plane to a surface. That tangent plane is spanned by, the vector is associated with the tangent space to the surface. So we can think of these M's as being associated with a tangent space. And we'll think of that conceptually this way. So we're at a given material point P. We've relaxed the body down to zero stress. Say we have crystalline material, for example, a cubic crystal, just to illustrate the idea. It's distorted here because it's stressed. We relax it to zero stress. It assumes its perfect crystallographic cubic shape, let's say. But this will not exist as a global configuration, right? We could have a dust cloud of infinitely many little cubes in Euclidean space, or we can imagine at any material point, this cube, or we could think of being associated with these three vectors, is the tangent space to a global manifold, but it's simply not Euclidean anymore. Okay, and we map that in material point back into the reference configuration by this K tensor, the inverse of G. So this is a Euclidean, a global configuration in Euclidean space, the reference. Kappa T is a global configuration in Euclidean space. But this relaxed state, stress-free state, can only be global in a non-Euclidean space. And so I can't see it because our eyes operate, are trained to recognize objects in Euclidean space. So I have to regard it as a kind of a local concept tangent to a global non-Euclidean manifold. So we think of this intermediate state as being associated with an undistorted crystal lattice because it's stress-free. If you remove all the stress from a lattice, it will it'll be in its so-called undistorted or minimum energy state, where it's a perfect crystal lattice like a cube. And that tangent space is a vector space. Okay? It's again tangential. A vector space that's tangential to our non-Euclidean manifold. It's not a configuration in the usual sense in Euclidean space. If we insist on thinking of it as a configuration, well then you can do so, but it resides in a non-Euclidean space. Okay. So remember we said before that plastic deformation doesn't affect the lattice structure, right? The plastic slip will preserve the lattice structure and therefore preserve the elastic properties of the material. So we can codify that in the theory by saying that there's the strain energy associated with any subvolume, let's say, of the current configuration. We can introduce a strain energy. It's convenient now to introduce a strain energy per unit current volume. And that will depend on the elastic deformation alone. If you remember in the first lecture, we introduced the notion of an energy, which was something like, for a linear elastic response with a Young's modulus and small elastic strain, it would be something like 1/2 the modulus times the square of the elastic strain. And the elastic strain was natural log of the elastic stretch. So ultimately, it's an energy that depends on the elastic stretch. Here we're doing exactly the same thing. We're taking the energy to depend only on the elastic deformation, the elastic part of it, and we'll take it to be per unit current volume. We can always do that. It's not convenient for analysis, but we can certainly define an energy per unit current volume. And in order to encode the idea, embed the idea that, see, this energy then tells us the elastic properties of the material. To encode the idea that the elastic properties should be insensitive to plastic deformation, just like the Young's modulus is in the uniaxial tension test, we should take that energy per unit current volume to be a function only of H, the elastic deformation. Okay. So this elastic deformation would represent the distortion of the crystal lattice. For example, in the case of a cubic lattice, the distortion of the cube required to fit it into, together with its neighbors, into our current configuration in Euclidean space. Okay. Do we need to pause for any questions, or are we okay with proceeding? I'll give you a moment to ask a question if you want to. All right, sounds like my explanation must be reasonably convincing, or you've just given up on me. I don't know.
Professor, actually I have a question.
Yeah.
Now for our whole analysis, we'll just take into consideration the deformation we had before due to plasticity, and now we just load the specimen again elastically. Are we going to analyze what's happening if we surpass again the elastic regime?
Of course, yeah, that's the whole aim of plasticity.
Yeah.
So this H will induce an elastic strain.
Yeah.
You'll be straining the lattice. That means we'll be stressing the lattice. And if we stress it too much, the material will yield.
Yeah.
When the material yields, that means it can undergo a plastic deformation, which means this K, or the G, which is the inverse of K that takes you from here to here, that will evolve.
Yeah.
And so the central problem of the whole subject is to figure out how to describe that evolution.
Okay.
So
yes.
there will be an evolution in K in response to sufficiently intense elastic strain. Okay.
Yeah. Thank you.
So please don't lose heart. We're building up exactly to that. Okay. But nevertheless, the strain energy in the crystal is due to elastic deformation. That's all I'm saying. Okay. Okay. Suppose we have a single crystal. So a uniform body or piece of a body composed of a single crystal. In this case, we would expect this function to be the same for every point in the crystal. The same, a uniform crystal should have a uniform constitutive function associated with it. So we'll focus attention on that, at least for the time being, to say that the strain energy psi per unit current volume is independent of the material point. It's the same function at all material points, okay? This is a notion we call material uniformity. So we'll use the same constitutive function at every point. Implicitly, then we're talking about a uniform crystal, or we're inside a crystal, the grain of a polycrystal, okay? So a polycrystal you can think of as composed of many grains. In the interior of each grain, we have a uniform crystal. So this argument would then, this would apply in the interior of a grain. Okay. Of course, the material point does appear implicitly because h varies from one point to another as you deform the body. The elastic deformation can be different for different points in the body. And so it can depend on p through its reference position, because p and reference position are the same thing. You identify the particle, the material point, by its reference position or by its convected coordinates, if you prefer. So this will be a function of material point through h, but that's an implicit dependence on the material point. Not, what I'm saying here is, we'll assume for the time being that psi does not depend explicitly on the material point. Okay. So here we've taken this function to be insensitive to g, the plastic deformation, simply to embed into the theory the notion that the undistorted lattice structure is unaffected by plastic slip. That goes back to G.I. Taylor in the 1930s experiments. Okay, of course, we can introduce a strain energy per unit in reference volume as well, right? Just by doing the usual change of variable from the current configuration of the reference by introducing the J factor, the determinant of F. So D small v is JT capital V, and that then I can use that to define a referential strain energy density, as we did when we talked about elasticity, pure elasticity. So this would just be J, I'll call it J sub F, because we're going to have a lot of tensors now. We're going to have three tensors whose determinants we have to worry about, F, G, and H. So I'll use the notation J sub A to mean the determinant of tensor A. So JF is the determinant of F, the usual determinant of F. So then this defines a strain energy per unit reference volume, no problem, okay? This now involves the plastic deformation as well, right? Because det F is H times G, det F is det H times det G. So psi will depend on the plastic deformation, just by the way we've defined it, even though psi does not. So the idea is the physical properties of the crystal are encoded in this small psi function. This definition of a referential strain energy density is an artifice. We do it only so that for our own convenience, right? It has nothing to do with the physics of the crystal. The physics of the crystal are encoded in this small psi function. If we insist on having a measure of strain energy per unit reference volume, then we're stuck with this factor J sub F, the determinant of F. The only reason we would do that, we make that insistence, is, for example, in the mechanical and energy balance, we need a material derivative of U, and for that purpose, it's more convenient to operate on a fixed domain, right? Okay, so this is just a definition then of strain energy per unit reference volume. Well, having done that, why don't I make a definition of a strain energy per unit intermediate volume? Instead of going from the current to the reference, why don't I go from the current to the intermediate? The problem there, of course, is there is no intermediate volume in our Euclidean space, right? There's no, the intermediate state is a cloud of dust in a Euclidean space. And there's no volume associated with that. We cannot define a volume in that space, right? But we can, nevertheless, if we look at this definition here, we can imitate this definition, and in place of J sub F, we write J sub G. G is well defined, even though there's no volume, intermediate volume. G is well defined, and we can take its determinant, right? So then this would define, just as capital psi here is related by JF to the strain energy per unit current volume, the same capital psi would be related by J sub G to a strain energy per unit intermediate volume in quotes, even though there's no volume. This definition still makes perfect sense mathematically. Right? Okay. So this function W, let's see, what is it? Well, it's 1 over jg, which is okay because g has a positive determinant, times this, which is j sub f times my original small psi of h, jf, let's see, jg inverse is jk because k is g inverse. So the determinant of k would be the determinant of g inverse, which is reciprocal determinant g. So we have jf times jk, but f times k tensor, f times tensor k is tensor h, so the product of the determinants is just the j of h, determinant of h, times energy per unit current volume, which is a function of h. Everything here on the right now depends only on h. So what we've done is to introduce a function w per unit intermediate volume in quotes, and it depends only on h also. So it stands in the same, so if we were doing pure elasticity, so there was no g was the identity, pure elasticity, go back earlier in the course, we talked about only elasticity, then this would simply be the strain energy per unit reference volume. Okay, so the reason for introducing this W is that we can carry over everything we know about pure elasticity just by using this function instead of psi. So then, let's see. To get the referential energy density, we do this to our W. J sub G is the reciprocal of JK. So this now, by writing H as Fk, we have psi is a function of F and K, because this is det K 1 over. This can be written as this is a function of F and K, right? So we have the referential strain energy depends on not only on F, but also on K. Again, I remind you, this referential energy is a purely mathematical construct that we introduce to make it easier to handle material derivatives in balance laws, that's all. The physics is encoded in this W or in the psi, the small psi, the physical properties of the material, the crystal. Notice that for a fixed plastic deformation, let's say one that does not evolve in time, so you plastically deform the body and then you don't induce any more further change in the plastic deformation. In other words, you don't yield the material any further to cause a plastic deformation to change. Then this would be some fixed function. Put that in here. The jk becomes some fixed function of x because it's det k. So we have now a function of f depending parametrically on x, right? So if for a fixed deformation, for a fixed plastic deformation, the referential strain energy looks just like that for a conventional elastic material, which is non-uniform because there's an explicit x dependence. So you can think of a fixed plastic deformation as producing a conventional elastic strain energy function, referential strain energy function, which, however, is different for different material points because of the explicit x dependence. And we allowed that possibility in our earlier discussion of nonlinear elasticity. That theory was set up to handle this possibility of a non-uniform psi, if you look back in your notes. It's a function of f, but that function of f could vary from place to place in the reference configuration. In other words, vary from one material point to another. And that's if we assume, let's take the plastic deformation to be fixed here. When we do that, we just get elasticity, but a non-uniform kind of elasticity. Okay? Well, if we go back to our earlier discussion of conventional elasticity, whether it's uniform or not, remember we proved that the symmetry of the Cauchy stress is equivalent to the invariance of the referential energy under a rotation superimposed on F, any rotation Q. So if you look back at that discussion, we had this result. Of course, this psi is just by definition given here. This psi, we're fixing the k in this discussion, so we don't change jk. We're just replacing f by qf, right? So if we look at this outer equality, you can multiply through by the fixed j sub k, and you just get w at h, which is fk, is w at q fk, which is w qh. So we have then the idea that this constitutive function w of h we've introduced should also be invariant with respect to superposed rotations, the same one associated with f. Okay. Now we'll come back to this discussion a little bit later to allow the possibility that k is not fixed. In other words, what happens if plastic deformation evolves in time? Then what? Let's stick with this example for the time being. Okay, we know how to solve this problem. We can polar decompose h in the usual way into a rotation factor and a stretch factor. Since this is good for any rotation q, we can pick q to be the transpose of the rotation factor in the polar decomposition of h to conclude that w must depend on h through the right Cauchy-Green deformation, h transpose h, or equivalently through the strain that you produce from that right Cauchy-Green deformation, right? So we had this exact discussion, if you look back in your notes on nonlinear elasticity. This is the reason why I had that discussion about nonlinear elasticity, precisely to get us to this point. Okay, so here we have an elastic Cauchy-Green deformation, and we can define a strain tensor based on that, so that when we're in the intermediate configuration, in other words, when h is the identity, so f then becomes g. When h is the identity, this strain disappears. So this is 0 when we're in our local relaxed state. Okay. So as usual then, the strain energy depends on the strain, in this case the elastic strain. So don't confuse this with the overall strain based on f transpose f. rather than put in all the subscripts to distinguish them, I'll just from now on write E as the elastic strain, okay? Okay, we know from what we've done before, for example, dWdH, just by analogy with what we did before, right? D psi dF was the Piola stress, and that's, Piola stress is F times the second Piola-Kirchhoff stress. So d psi dF is F times S. Well, we can do the same thing here exactly, just by repeating that argument. D psi dH is H times some kind of second Piola-Kirchhoff stress based on this kappa I intermediate state as reference configuration. This is not the second Piola-Kirchhoff stress based on the reference configuration. It's based on this kappa I, not on kappa R. And we know from going back in our notes here to these pages 21, 22, that S is just the derivative of this strain energy with respect to the strain, symmetric, okay? Okay, we also know, so this would be like a Piola stress relative to the kappa I instead of kappa reference. We know how to relate the Piola stress to the Cauchy stress. Take the Piola stress, Piola stress is Cauchy stress times the cofactor of F, except here, in place of F, we have H. Piola stress, based on the intermediate, is Cauchy stress times the cofactor of the deformation that takes us from intermediate to current, which is H. So that star is the cofactor of H. T is the Cauchy stress, which is defined on the current configuration, right? So as usual, the Piola stress, which is the derivative of capital psi with respect to F, right? We're looking at K fixed here, this whole discussion, for the moment, only for now. As usual, that's T times F star, right? But we have two expressions involving T here, so we can relate these objects to each other. So the WDH is T H star, H is FK. I'll leave it to you to prove that the cofactor of a product is the product of the cofactors in the same order. Unlike the transpose, right? The transpose of a product is the product of the transposes in reverse order. The cofactor involves the inverse transpose. And the inverse of a product is also the product of the inverses in reverse order. So you have two reversals that bring you back to this. So the cofactor of a product is the product of the cofactors without reversing the order. That's a small thing to prove, and I encourage you to do that in your notes somewhere. So FK, all cofactor, is F star, K star, product of the cofactors. This TF star is our Piola stress, the conventional Piola stress based on the reference configuration. So the WDH, the Piola based on the intermediate, is the conventional Piola times the cofactor of K. Conventional Piola is the capital psi dF K star, okay? Okay, I think I can fit in one more item before we leave today. Remember, we talked about the Legendre-Hadamard inequality. Conditions we would want our strain energy function to satisfy so as to admit the existence of, say, stable equilibrium states, which are, of course, experimentally observed, right? And I think that's page 26 if you go back in the notes, and you had a handout about that. And of course, you've just done a homework about it also. That discussion was this: whether the capital psi has an explicit X dependence or not didn't matter. Take two derivatives of the referential energy with respect to F, and you have, for arbitrary vectors A and N, you have this scalar being non-negative for all choices of A and N. That's a necessary condition that our Fs should satisfy, right? Well, the theory now is based not on psi. The physical content here is encoded in this W of H. So we'll go back to this equation. So this inequality involves two derivatives of f. Let's see if we'll take an h derivative of this at fixed k. So in this discussion, we've fixed k. And let's consider, say, a one-parameter family of h's, h of u, f of u times k. One-parameter family of f's, k fixed, you get a one-parameter family of h's at fixed k. And then we'll differentiate this equation A here with respect to the parameter. When we do that, we get the derivative, we get, I'll say a derivative with respect to u, I'll call it a dot derivative. WH all dot would be, by the chain rule, d squared w dh squared operating on h dot. H dot would be f dot k from this because we're fixing k. We have to take a dot also of the right-hand side. That would be with k fixed, therefore k star fixed. That would be d squared psi df squared operating on f dot. Okay? So we have this result. Let's now take an inner product with f dot k. We do that here. We have the k star. So here we have this, the structure of this is two tensors, BC, inner product, a third tensor, A. So after all this operation here, however complicated it is, we have a fourth order operating on a second order, the f dot. That gives you a tensor, a second order tensor. Multiplying a second order tensor gives you a second order tensor. So the structure of this equation is BC dot A. So that's the same as A dot BC because the dot commutes. In the trace definition, that's trace of A times the transpose of BC, which is C transpose B transpose. And that's the same as AC transpose inner product B. So that means, let's put the A in front. Multiplied by the transpose of C, which is my K. And then take the dot with B, which is F dot, which is right here. And all I've done is then commute the dot product, right? This is the same as B dot AC transpose. So you're going to get a K star K transpose, which is just determinant K times the identity, because K star is JK K inverse transpose. So you're going to get JK times F dot times this. Let's go back to our Legendre-Hadamard condition. What we've just done involves F dot, right? Let's choose F dot. F dot is arbitrary here. Let's choose it to be A tensor product N, where A and N are vectors. When we do that, we get A tensor product N operating on K. I'll write that as A tensor product K transpose N. And I'll call it M, not related to my M sub I from the previous discussion. This is K transpose N, where N is arbitrary. So M is also arbitrary to the same degree that N is arbitrary. Then I get d squared W dH squared, get A tensor product M. Then I get this, but this is non-negative by the Legendre-Hadamard inequality. So that means W of H also satisfies the Legendre-Hadamard inequality. Arbitrary A, arbitrary M, greater than or equal to 0. Okay? Okay, so we'll pick this up next time to discuss a realistic restriction that we should put on the function W of H, or equivalently on the function U as a function of the elastic strain. Okay, let's stop there for today.